Hello, everyone. My name is Xixu Hu, and today I would like to introduce you our latest publish in ECCV 2024. It is about guarding vision transformer robustness via maximum singular value penalization. So we know that neural networks are powerful, but are they robust? And the answer is no. So we can easily craft perturbations that are imperceptible to the human eyes, but can greatly disrupt the neural network decisions. So here I showed an example of the adversarial attack. You can see we have two images of the panda. They look almost the same to our eyes, but the neural network will classify them differently, just because we inject an unperceivable adversarial attack here. So for the adversarial attack, they want to incur the training loss as much as it can under a predefined budget. So how to counter it? And the most effective method nowadays is adversarial training. So unlike standard training, adversarial training will play a minimax optimization game. So in the inner loop, we will optimize the perturbation to incur as large as training loss as it can. And on the outer loop, we will optimize the parameter, try to reduce the influence of the perturbation. So what do we want to do in this project? In this project, we want to develop an enhanced method to strengthen the robustness of vision transformers. So we start from a classical concept in mathematics, that's the Lipschitz continuity. So why we focus in the Lipschitz continuity? Because we notice that it is greatly fit the scenario of adversarial robustness. So for the adversarial attack, the input perturbation has been relatively small due to the perturbation budget. So if we can further optimize the Lipschitz constant on the right-hand side, then we can control the output changes on the left-hand side, which means even under input perturbations, the output result will not change too much. Thus, it will still give a correct classification result. So we delve into the meticulous analysis of the attention mechanism, and we derive a local Lipschitz constant bound here, which shows we can control the local Lipschitz constant by optimizing the right-hand side. That's the maximum singular value of the Curie key and the value matrix. And because we can control the local Lipschitz constant by inspired by the Lipschitz continuity bond, we can further enhance the robustness of the left-hand side, and we can reduce the sensitivity to the perturbations. So we developed the corresponding maximum singular value penalization to enhance the robustness of the vision transformer. And our model that's employed layer-wisely the maximum singular value penalization, we call it SpecFormer. So we validate the performance of our proposed SpecFormer in 4 classical robustness benchmark, that's CIBA 10, CIBA 100, and ImageNet. And also we test the efficacy of the penalization under two training methods, that's standard training and adversarial training. And we select string baseline, which all achieve Lipschitz continuity through various modifications, together with the vanilla VIT as the baselines. And we validate across string VIT variants, that's the def-IT, conf-VIT, and the swing transformer. And for the evaluation on attacks, we evaluate on FGSM and the PGD2 for standard training, and we evaluate on CW20, PGD20, and auto attack for adversarial training. And the result is shown here. The best accuracy are in bold, and we can see that our SpecFormer achieve the best results in most of the cases across datasets and the VIT variants. And this works the same for the adversarial training. At last, we show the time efficiency of our proposed model together with the baseline, and we can see that our SpecFormer incurred the lowest additional computation cost. And finally, I show some experiment analysis of our model, and we can see on the left-hand side, our SpecFormer can effectively control the ellipsis continuity of the VIT. And on the right-hand side, I plot the TSNE plot of vanilla VIT and SpecFormer. We can see that the adversarial samples and the clean samples are aligned better within each class, within each cluster for our SpecFormer, which means even under perturbed samples, our SpecFormer can also correctly classify it into the correct type. So that's all for my presentation. Thank you for listening, and all questions are welcome.